In this video, I'm going to show you how you can use the periodic table to provide some information regarding the first two quantum numbers about certain electrons in an element. And I'm also going to show you the basics about writing out electron configurations. In the next video, I'm going to delve more in depth into writing out electronic configurations, but I'm going to start in this video by basically just kind of showing you the basics of the notation that we use for that. So first, when referring to the quantum numbers that you can identify, I'm talking about the valence electrons. So the valence electrons are just the electrons in the outermost shell, so they're the outermost electrons in an atom, which means that they're also the highest energy electrons in an atom, because as you go further and further from the nucleus, the energy that each electron has goes up and up. So for the valence electrons in any element, just by looking at the periodic table, you can figure out some information about the first two quantum numbers for them. So talking about the first quantum number, n, you just have to look at what row it's in. Remember, the rows are referred to as periods. So if I can just number them, starting at the top and going down. 6, 7. So for instance, let's look at sulfur. Sulfur is in the third row, the third period. So that means that the valence electrons, the outermost electrons in sulfur, are in the third, have a principal quantum number of 3. So they're in the third energy level. Looking at tellurium, for instance. Tellurium is in the 5th row on the periodic table. So its valence electrons have a principal quantum number of 5 and are in the 5th energy level. Simple as that. When talking about the second quantum number, the azimuthal, you have to look at what block it's in. So what do I mean by that? Well, the periodic table can be divided into 4 different blocks. So these first two groups form what's called the S block. So right there above, S block. And where this S comes from, if we go back to what I was telling you about last video, comes from the letter designation for the value for L. So being in the S block, that means that the valence electrons for any of the elements in these first two groups, oh, and also helium. So helium is an exception, that helium is also part of the S block. All right, so I'll just say S as well. So their valence electrons in those have an L value of 0. The next one after that, for an L value of 1, so that's represented by the letter P. In the P block are all of these ones on the other side of the transition metals. Of course, again, not including helium, because helium is part of the S block. So this right here is the P block. So all of the valence electrons for anything here have an L value of 1. So for instance, looking at S, so sulfur, right? So I already said that sulfur had an N value of 3 for its valence electrons. So it's got an N value of 3 and an L value of 1. Magnesium, on the other hand, is still in the third row. So it has an N value of 3 also, but it's also in the S block. So now it's got an L value of 0 for its valence electrons. After P is D, so for an L value of 2. And the D block is represented by your transition metals. So this right here is the D block. And one important thing to remember is that these two rows down here basically just get pushed right into these two spots, and these first two, lanthanum and actinium, are still included in the D block. So these are the first two here in the D block. And then lastly, after D, an L value of 3 is represented by the letter F, and the F block is just what's remaining, the rest of these two groups down here. So that is your F block. Alright, so basically just based on the location, again, of an element on the periodic table, you know where its valence electrons are in terms of the first two quantum numbers. There is no way to determine the second two quantum numbers just by looking at the periodic table. But if we talk about the third quantum number, if you remember, so I said that the third quantum number can go from negative L to positive L, right? So again, if L is 0, well, negative L to positive L, if L is 0 equals 0, m sub L can only be 0, which means m sub L only has one value, right? So that means that there's only one, and remember, m sub L tells you the orbitals, so that means that there's only one orbital, because there's only one value for m sub L, if L equals 0. And each orbital, remember, if we look back at the last spin, or the spin quantum number, the last quantum number, each orbital can contain 2 electrons. So if the L value is 0, and there's thus only one orbital, there could be a total of 2 electrons in that subshell. So here, let me kind of draw this out a little bit to show it a little bit more. So let me grab another sheet of paper. So again, if an L value equals 0, m sub L can only equal 0, which means that it can have an m sub s of plus 1/2 or minus 1/2. M sub s equals minus 1/2 equals. So that means 1, 2. Only 2 electrons can exist if your L value is 0. If your L value is 1, that means your m sub L could be, so I'll say m sub L up here, it can go from negative L to positive L. So there are 3 different m sub L values, which means that there are 3 different orbitals present. Each orbital, again, can have 2 electrons. So each orbital can have a plus spin orbital and a minus spin orbital. So we've got plus 1/2, minus 1/2. This is plus, this is minus, this is plus, this is minus. So that's 1, 2, 3, 4, 5, 6. So there can be 2 electrons up here, as I said, right? And again, if L is 0, that means that it's an S subshell. Here, in a P subshell, which is when L is equal to 1, we can have, again, 1, 2, 3, 4, 5, 6 total electrons. Now let's talk about a D subshell, where an L equals 2. That means that m sub L can go from negative 2, negative 1, 0, 1, or 2. And again, each one of those can have 2 electrons, one with a positive spin, one with a negative spin. So in a D subshell, you can have a maximum of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And lastly, for an F subshell, which is when L equals 3, it means m sub L could be negative 3, negative 2, negative 1, 0, 1, 2, 3. Now, again, one last time, each of these can have 2 electrons, one with a positive spin, one with a negative spin. So that means in an F subshell, you can have up to 14 electrons. But you don't have to remember this information, because you can actually just look at the periodic table. So looking at the periodic table, I said that an S subshell can only have a maximum of 2 electrons. Well, if you count along each row in each energy level, 1, 2, 1, 2, 1, 2. Each energy level only has 2 spots in the S block, and each one of those gets an extra electron. So that represents the 2 electrons that can be in each subshell. The P block has 1, 2, 3, 4, 5, 6 elements in each row, in each shell. So that represents the 6 different electrons that could be present in a P subshell. The D block has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which correspond to the 10 electrons that I mentioned are possibly maximum in the D block. And the F block, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you can actually just remember how many electrons they can have by looking at the periodic table. And that will actually be useful again in the next video. But just to finish off this video, I want to talk about the basics of the notation used for writing electron configurations. So electron configurations will look something like this. So there's basically going to be three useful pieces of information here. This first number, so this is 1s2 here. This first number is just your n quantum number. So that tells you that that electron is going to be in the first row on the periodic table, right? This s is your L quantum number. So that's going to tell you that it's going to be in the s block, which, of course, if it's in the first row, both of them are in the s block, so that has to be the case. But yeah, so that'll tell you which block it's in. And then this number up here is the number of electrons. So this means that there are 2 electrons present in the L subshell of the first energy level. Right? And that's the notation we're going to delve in further in the next video.